No, Professor.
Hello there, you can hear me?
Yes. How are you, Professor Krauss?
I'm
It's good
fine,
to see
thank you very much. I just finished preparing my talk about 5 minutes ago, so.
you. And actually, we went a little bit quick, and the others finished earlier.
Ah,
Uh, by, yeah, by that time, we share your information to the participants. By
I
the way,
see.
this
I'm sorry. I should have come, if you'd sent me a note, I would have come on earlier, but
it's
okay.
okay. Yeah, we are expecting that you will come on the time, and this is what happened.
Okay.
Thank you very much that you are here.
Well, it's nice.
As I shared the information about you on the screen, you are one of the legends of the physicists, the currently in the literature, and it's very obvious from your the background and the prizes and the awards that you received. I am really excited to see you here again. And this is a hybrid conference, and there's also a face-to-face part in the Canada. And if you check your the WhatsApp, I shared that there is a room that they will also watch this conference in that room as well. So welcome, first of all.
Well, thank you.
And
It's an honor.
let me yes. Is it possible to share your screen and
Yeah, I was going to share. I cannot share while you're sharing. Okay, now I think I
okay,
can.
let me
And I want to share, I'm just going to share my keynote presentation, okay? Is that all
sure.
right?
Wait a minute. Let's see.
Hold on, let me just stop this.
I think you can share now, am I right?
Okay, I'll share in a second. Hold on. Okay, I'm going to try and share. Now I share. And here we go. Okay. Um, Now you see a sort of a blank screen, more or less?
Yeah, your screen shared.
Yeah. Okay, good. Okay, good. I'm screen sharing. Should I begin or should I wait till the exact time?
Professor Behnan, what's your opinion about
Should
that?
I? Yeah.
Maybe
And
we may wait 5 minutes.
yeah,
If
sure. Okay, well, at least
yeah,
that's on there so people can see that and then they can
No problem. You
we'll
can
begin
start.
we'll begin in 5 minutes. It's no worries. And it's nice to be there. I assume I don't know where everyone is from. I assume
worldwide.
what was that?
Worldwide. The
Yeah,
audiences are
worldwide.
from
I know,
different.
but
Yeah.
there, yeah, but it'd be nice to know where people are from. There's only 15 people or so, so I could find out where people are from.
But as I mentioned, some of the people are in the room in Canada because these
Oh,
yeah.
oh,
So
okay.
they're
So
watching
they're in
over
the
there,
room.
I'm sure.
Oh, okay. They're in the room. Well, one of my collaborators is I think at the institution where the room in Canada is being done, and in my work on fluids, but gravity and fluids is there in British Columbia. Is that where it is in Canada?
Mir Faisal.
Yeah. Okay. Yeah. Well, it's nice to see some people are here for this, which is good. Um, and you're from, of course, from Cyprus, and
Thank you. And yeah, Huriye and Mert are also here.
and Bam is from Iran. Is that right?
Yes.
We have people from Iran. Well, so we have people from Iran and Cyprus and Canada. Any other places?
We had some Chinese, but I don't know whether they are here or not. Apparently, yeah.
Okay. The whole conference has been essentially online. Is that correct?
Could you repeat it again?
The conference has been online. Is that correct?
Yeah, online, and as I said before, there's a room in Canada, and actually that's the part of the face-to-face part. And these people will watch you on the screens that they prepared. If you check your WhatsApp, I shared the room that they sent us.
Oh, I didn't
Most
check. Oh,
probably,
that's nice.
they were waiting you. Now they were few, but it will be increased, I'm sure.
Okay, it's on my WhatsApp?
Yep.
I will look for it right now. Yeah, I'll look for it right now. Okay. Oh, I see. Okay, I got WhatsApp. Here we are. You were just saying hi to me, probably worried that I wasn't going to show up an hour ago, 2 hours, an hour ago. Okay, good. I see the, oh, I see the room. I see a picture of the room.
Yeah, we have. That was the photo 50 minutes ago, which was sent to us.
Okay, good. Okay. Well, it looks like another 2 minutes, but we should wait till exactly the right time, probably in case anyone.
Thank you.
Yeah. No,
How is Canada?
I was worried that my timing was wrong because you had this being at like something like 8:30 or 9:30 for me, but it's 12:30 here. So I checked the GMT time and I figured that was the correct time. So
Yeah, thank you. Yeah, we know that the time is not very good for Canada
yeah, well,
time.
you know, it's hard to know. That's the biggest problem with all of these meetings, that international meetings that I often have in Zoom meetings, is getting the time right. Because some people have daylight savings time and other people don't, and some people have an extra half hour. And yeah, so it's nice to see I actually showed up at the right time, which is a good thing. And how's the weather? Is fine here in Canada. Hope it's all good where you are.
Here the weather is 40 degrees.
Yeah,
40,
well, I remember
42.
from even when I left there,
Yeah.
40 degrees. It's a little too hot for me, but here it's
But
22.
currently it is hot for us.
Yeah, it's about 22 degrees here today.
Oh, very nice.
Watched. So it's a little bit more. And in Iran, I don't know what the temperature is. It's
Man,
probably hot there too.
what's the weather over there?
He's not got his microphone on, so.
Yeah, he's making some arrangements. Is there anyone to tell us the weather in Iran now? Everyone says too hot.
Very hot, very hot.
Very hot.
Very hot, very hot. Okay, well, he says.
Oh.
But Damghan in night is very cool.
Mm.
Okay,
Day
well,
very hot, night very cool.
well, I hope it's good. Well, I hope it's we can get this done, and then you can have a go somewhere. I hope it's air conditioned wherever you are. And yeah, I prepared the talk to be short with the time for a few questions, and then as our invitation, so that hopefully we'll go a half an hour or less. We'll see. It's a pleasure to be here. Really, truly, it's an honor to be invited, and I'm happy to be part of it. To those of you in Canada and those of you elsewhere, thank you for being here. I guess it's 12:30, so I guess I can begin. Is that okay?
Yes, it's okay. You can start. Thank you very much.
Okay, well, thank you for the nice slide beforehand showing some of my books and other things and a few awards and things. I was a little hesitant to accept an invitation to a conference on holography and its applications, since I really haven't worked on holography directly in its applications. But I have worked on some areas that will be relevant, I think, to the issues that holography addresses, at least in the context of quantum gravity. And so I thought I would talk about that work that I've done, 3 different topics that will be relevant, I think, in the long run to potentially addressing some of the issues that we want to understand with holography, which is how to understand a full quantum theory of gravity. And so anyway, so there are 3 different topics, and we'll proceed. So the first topic I wanted to do relates to 2 of the 3 topics that I'm going to talk about were actually work done with my junior colleague Frank Wilczek. and not really my junior colleague, but different works that has been done over the years. And then the last one is, in fact, work that's been done more recently with colleagues, including some colleagues at the institute where you're watching from. But the first one involves a key question, which is we spend a lot of time worrying about quantum gravity, but we don't even know if gravity is a quantum theory. For sure, there's no evidence of that yet. How might we provide, is there any way other than detecting gravitons, and Freeman Dyson has argued that you can't detect gravitons directly with a detector. I'll point out that the universe will allow us to detect gravitons, but it's hard to know, short of having either a theoretical full description of quantum gravity or some experimental detection of gravitons, to know whether gravity is really not just a classical theory, and perhaps at fundamental scales it's quantum gravity, it's quantum mechanics that needs to be modified and not gravity, as some people like my friend Gerard 't Hooft and others seem to think. In any case, I want to show you how the universe could, if we're lucky, provide us a way to actually prove that gravity is a quantum theory. It involves a little bit of cosmology, but since that is an area I work in, I thought I'd talk about it. And it involves one of the miracles of inflation that we don't talk about very often. And that is that in inflation, if inflation is true, then everything we see is really a manifestation of quantum fluctuations. In inflation, there is a potential, and as you know, and the universe in this case is in a false vacuum state, and eventually a phase transition happens to when it goes to the true vacuum state, and the field reheats. And of course, in this state, which has a height which is proportional to the square of the Hubble constant at the time, there are quantum fluctuations. There are always quantum fluctuations, and the magnitude of the fluctuations in this field is proportional to the energy scale of the field, just by dimensional analysis, but it works out to be true, that the magnitude of fluctuations in this field is proportional to the height of this potential. The bigger the potential, the larger the fluctuations. That actually is a mechanism to produce everything we see in the universe today. Because what happens is that inflation ends, but because in different points in the universe, the field is at a different position on this flat plateau because of quantum fluctuations. In some regions of the universe, it's closer to the fall off, and in some regions of the universe, it's further from the fall off. And that means that different regions end inflation at different times. But those that have ended earlier begin to redshift. The energy density in those regions begins to redshift. Those that enters later, that energy density hasn't redshifted. So that means there's an energy density differential between the different regions that depends upon the time in which they left inflation. And that allows you to heuristically show that you'll produce fluctuations in energy or in matter that are proportional to two things. First of all, the larger the scale of the potential, the larger the quantum fluctuations, and therefore the larger the time difference between different fields before they leave inflation. And then that's in the numerator, and the denominator is the slope of the potential. If the potential was exactly flat, then it would a field that was over here and suddenly dropped off would leave an infinite amount of time earlier than a field over here, so fluctuations would be infinite. If the potential was extremely steep, then all fields would leave about the same time, regardless of when their small fluctuations were happening, and the energy density fluctuations would be zero. So this is a heuristic understanding of why inflation gives energy density fluctuations that produce galaxies and stars and planets and people, including physicists. And this gives you an example of how how you can understand this. Well, this is just one kind of fluctuation. All fields fluctuate in de Sitter space. And if gravity, well, that produces these, of course, this is the famous picture this is from Planck, I think, of the hot spots and cold spots in the microwave background. And inflation does a pretty good job of producing an initial spectrum of fluctuations that is Gaussian, as this looks like it is, And that is one of the reasons why inflation is a good candidate theory for the early universe. But if gravitational waves are also, if gravity is quantized, then there's the gravitational field is also exhibits fluctuations. Now, I reminded you that scalar fields have a fluctuation, their fluctuation, the square of their fluctuations, magnitude of fluctuations is proportional to the Hubble constant at the time. But there's a famous fact that if you look at gravitational waves, those two helicity states follow an equation of state in the background expansion of the universe that looks just like a scalar field. Each helicity state of the gravitational wave follows an evolution that looks like a scalar field with, of course, something that gives you the right dimensions, the Planck mass and the scale factor. So that means if scalar fields fluctuate, then the two helicity modes of gravitational waves fluctuate, and in particular, the two gravitational modes of gravitons will fluctuate. And you'll get an amplitude of fluctuations in the gravitational field, or in which is proportional to h squared, and the constant proportionality, in order to have units right, is proportional to Newton's constant. And that will be proportional to the scale of the potential, or if you wish, the fourth power of the scale of inflation. So this tells you that gravitational waves themselves, gravitational field itself is fluctuating, and the higher the scale of inflation, the larger the fluctuations. So it tells you that during inflation, gravitational waves will be produced, and it's a generic prediction of inflation. And we hope, I was going to go into explain how we look for it. Well, I guess I'll give you one example of how we look at this. But first, let me tell you that I told you that scalar density perturbations, the density, depends upon the shape of the potential. But tensor perturbations, which are perturbations in the gravitational field itself, are independent upon scale. They just depend upon the overall, they're independent of the shape of the potential. They just depend upon the scale of inflation. So it's really a generic prediction of inflation. If we're lucky and the scale of inflation is high enough, then the amplitude of gravitational waves will be high enough for us to detect it. Unlikely that we'll ever detect it directly with gravitational wave detectors, at least in our lifetime. But the universe is a gravitational wave detector, because if you think about this, the cosmic microwave background is caused by radiation scattering off electrons. But if a large gravitational wave goes through this region, it squishes the size of the region in one direction and stretches it in another. That means the intensity of the radiation is higher coming from this direction than from this direction, and that produces that scattering, therefore, because the intensity is higher in this direction than this direction, produces a polarization in the outgoing waves. And by looking for polarization in the microwave background, we might, if we're lucky, detect a signal of gravitational waves. It's a very particular type of polarization, and I won't go into the details here. Once I think in 2015 or so, maybe 2014, we thought we discovered it. Not we, but an experiment called BICEP thought they discovered this signal, and they hadn't. But if we're lucky, and that means we have to be very lucky, the scale of inflation will be high enough so that the remnant signal will be detected in polarization measurements of the cosmic microwave background. We'll see. Now, why am I talking about this here? I'm talking about this here because it will allow us to show that quantum gravity exists. Because as I said, gravitational waves from inflation arise as individual graviton fluctuations, at least in the calculation I described. But of course, classical effects can always be calculated quantum mechanically. Quantum mechanics is the fundamental underlying theory of the classical world. So the fact that you do a quantum calculation does not imply that the underlying phenomena relies on quantum mechanics. If it relied on quantum mechanics, it would vanish in the limit of h bar going to 0. And the question is, does this effect go to 0 in the limit that h bar goes to 0? And in fact, we can show that it does. And this is the work that Frank and I did. by the simplest of possible arguments, a first-year physics argument using dimensional analysis. The energy density in gravitational waves produced by inflation scales as the 1 over the 4th power of the scale factor, because it's radiation, and radiation scales as 1 over the 4th power of the scale factor while things are inside the horizon. To get a dimensionless effect, we have to compensate and multiply things by the 4th power of the scale factor. And so this is a dimensionless quantity. And the energy density in gravitational waves has the units of energy over length cubed, of course. And then the scale factor has units of length to the 4th. And so you can show that since energy is equal to mc squared, this has units of ml cubed over t squared. So this quantity is based on these dimensional parameters. But the only variables that allow us to determine in inflation the gravitational waves are the gravitational constant, the scale factor, h bar, and c. That's all that comes into the calculation of gravitational waves. So if we look at this and we allow these to have arbitrary powers, we can ask what power of these quantities will produce this dimensional result. And the answer is it has a unique solution. This is first order in the gravitational field, of course. It involves alpha equal 2, beta equal 2, and gamma equal -4. But you see, because beta is 2 here, this effect goes as h bar squared. And that means in the limit that h bar goes to 0, there are no gravitational waves generated by inflation. And this means if we are lucky enough to detect gravitational waves from inflation and prove that they're from inflation and not from some other background mechanism, then we will know that gravity is a quantum theory. It's an amazing result. It would require us to be lucky, but it would be amazing. We'd be able to prove that indeed gravity needs to be quantized, and that and it's not that quantum mechanics changes as we go to very small scales, but rather that gravity must be quantum theory. And that obviously is of great importance for those who are interested in holography when it comes to string theory or quantum theory of gravity. We don't have to worry about holography if classical general relativity is all we need. Well, we might. If we think about black holes, we still might want to try and understand the information loss paradox using holography, and I'll talk about that. Okay, that's the end of the first part of the talk. The second part involves something we might want to measure with holography, which is non-classical observables on black holes. A holographic picture of black holes suggests that all the information of what fell into black holes resides on the surface, on the event horizon. That postulate. Now the question is, are there observables that are not classical? In general relativity, the no-hair theorem tells us that the only observables associated with black holes are their mass, their charge, and their angular momentum, because those are the only observables that are tied to long-range massless fields. Okay, gravity and electromagnetism. As Frank and I showed in a paper now over 30 years old, but it'll become relevant again later. Actually, there are simple ways to imagine that black holes could have quantum properties that are not observable classically. And we invented something we call discrete gauge symmetry. And I'll describe it briefly here. It requires some thinking. So if you don't understand this when I talk about it, you can think about it. I have to admit that I'm not sure Frank and I even understood it when we wrote this paper. It's a subtle phenomenon. But imagine a U1 gauge theory with two scalar fields, eta and zeta. Now, eta carries a charge PE, and zeta carries a charge E. Now, if the field that carries a larger charge condenses, while the other does not, and it condenses at a very high mass scale, then something interesting will happen. eta has condensed, and so it's broken the gauge theory, gauge symmetry. But the low energy theory, because zeta has a charge E, it will there'll be a residual remnant of the gauge symmetry, which will say that the low energy field zeta is invariant under what appears to be a global symmetry. Zeta goes to e to the 2 pi I over p times zeta, that global symmetry. And that's a consequence of the original gauge symmetry. The Higgs field can screen out charges that are of order PE, but not of charges of order E, and that charge of order E will have that residual symmetry. Now, it is a residual gauge symmetry, even though I want to just go back here for a second. Because the theory of eta condenses at high energy scales, if you're at low energy scales and you can't excite eta, and the gauge field itself gets an extremely high mass, there's no evidence at the low energy scale that you have anything but a theory of a complex scalar field which has a global symmetry. So at low energy scales, the entire theory is that of a complex scalar field with global symmetry, because you can't see eta and you can't see the gauge fields. They have very large masses. But there's a fundamental difference. It's not a global symmetry. It's a residual discrete gauge symmetry. And the point is that nothing, including quantum gravity, can violate gauge symmetries. It's been well known that quantum gravitational effects you could imagine could violate global symmetries, could produce terms that violate global symmetries. But the point is, gauge symmetry is a very different kind of symmetry. A gauge symmetry tells you that the variables of the theory are redundant, that themselves they have no physical significance. The only significance are gauge invariant quantities. And therefore, the quantum gravity, because those variables are not physical, quantum gravity can't break that symmetry. At higher energies than m, the U1 symmetry is unbroken. So the Higgs field is there, but the Higgs field can only screen charges that are multiples of PE. So there exists at the high energy scale and even at the low energy scale a conserved charge. But when the theory is unbroken, there's a conserved charge modulo PE, just by Gauss's law. And that charge, it shouldn't be changed. That charge is associated with the observable e to the 2I charge over PE. Now, charge itself is not well defined because the Higgs field can screen the charge. But Gauss's law tells you can rewrite that as a surface integral. E to the 2 pi I surface integral of E dot ds divided by modulo PE. Now, that is an observable. The electric field is an observable. The charge isn't, but E dot ds is a globally observable quantity that you can get by doing a global surface integral. And because it's a global quantity, and because it's a surface integral, it can't be affected by the gravitational collapse of what's inside. So if there's some charges inside, some zeta charges inside, they collapse, that charge cannot be hidden by the horizon of a black hole because the surface integral is measured before it collapses and the surface integral is the same after it collapses. It's intrinsic to the black hole. It's a charge that you can't measure because there are no long-range gauge fields. There are zero, remember the field, the eta has broken the U1 symmetry, so there are no long-range gauge fields. But that hair still exists, but it's purely quantum hair. There's no classical way that you can measure that. How could you measure that hair quantum mechanically? I don't know if someone's drawing on I didn't draw that. Anyway, someone drew on that, but that's okay. I can live with that. How can we detect it? We can detect it by the ultimate gedanken experiment. This theory where eta breaks down, breaks the gauge symmetry, supports stable strings that are threaded by a flux 2 pi over PE. And those strings can scatter. Actually, if we have zeta particles with charge E, they will scatter off those strings. And because they're charge E and not PE, they can get an Aharonov-Bohm phase. So they can scatter off those strings. So let a zeta particle fall into a black hole and scatter a string from the black hole. You know, the scattering is going to be dominated by large times and distances and not relevant to the horizon of the black hole. It will not depend on what crosses the horizon. And therefore, you could imagine, I mean, it's the ultimate gedanken experiment. You can imagine that if you scattered a cosmic string off a black hole, and that's what I mean by the ultimate gedanken experiment, you could get Aharonov-Bohm scattering, which would produce a scattering of the string, which would be invisible classically, but it would tell you that there are zeta charges inside the black hole. So you could know that the black hole had quantum hair that wasn't observable classically. And this is this is just one kind of quantum hair. Other people have imagined other kinds of quantum hair. This may be relevant if we're trying to understand the information that falls into a black hole as encoded on the surface of the event horizon, because we may need to take, could be that all information is related to the quantum hair on the surface of a black hole that you couldn't see classically. That's one possibility. It may not be right, but it's one possibility. Well, this is a gedanken experiment, but I want to, in the last 2 minutes of the talk about ways that we might probe quantum gravity with real experiments. And that's an area that's become quite exciting lately, which is producing analog gravitational systems with fluids. And what I want to talk about here is whether we might probe quantum gravity using these analog systems. And this involves a paper that I did with Sam Brownstein and Mir Fazel and Francesca Marian and Navad Shah that appeared in Nature Reviews of Physics last year, and another paper that just came out this year that follows up on that. It's been recognized for some time that classical and quantum inhomogeneous fluid flows can reproduce effective metrics that mimic black hole physics. That if you have phonon trajectories in a fluid and the fluid is moving, those phonon trajectories, which are, they're moving at the local sound speed, if v is the velocity of the fluid, then those phonon trajectories are determined by this geodesic. But if the fluid is inhomogeneous, if it depends on x, then the phonons effectively experience a curved spacetime. And this allows you to create analog systems that mimic gravity. And numerous semi-classical analogs have been measured in laboratories with classical fluids and with Bose-Einstein condensate fluids. And the things that have been seen are horizons, UNRWA radiation, thermal phonon fluctuations with a temperature given by the surface gravity, as predicted by Hawking and Bekenstein, stimulated Hawking emission, quantum correlations between ingoing and outgoing phonon pairs at the horizon. If the fluid is moving faster than the sound speed, then you effectively get a horizon, and you could try and measure these phenomena, and also Penrose superradiance. So a lot of classical and semi-classical phenomena have been observed in these systems. And what we started to think about was, could you probe quantum gravity itself with these systems? And I want to just talk about that. We might be able to probe the black hole information paradox. How's information not disappear in these analog black holes? Look for gravitational back reactions and maybe the avoidance of singularities, because of course these systems have shock waves, but there's no singularities. There are physical mechanisms that stop the singularities. Will those be relevant to the mechanisms that might stop quantum singularities in quantum gravity, quantum hair? And I had to use the word holography, and I'll end up with holography. So I want to talk about two things, because I want to talk about quantum hair, because these systems might actually, if you're lucky, provide a mechanism to see that things that were once thought of in that just gedanken experiment that Frank and I thought of 35 years ago now. In fluid experiments, quantum hair could be mimicked by fields of purely quantum origin generated by topological defects or vortices in these systems acting on phonomic collective excitations that have finite topological charge. So you can get collective excitations of phonons that have topological charge, and you get vortices. And that gives you, in principle, if not in practice, the possibilities of observing Aharonov-Bohm scatterings, such as the phase shift of a classical wave with finite topological charge interacting with a vortex. Those classical signatures of this phenomena have been detected in water wave experiments, classical phase shifts, but not yet quantum phase shifts. But what if you could? The detection of the same effect in superfluids at the level of quantum excitations has not yet been achieved. But more recent experiments have demonstrated the ability of imprinting on-demand vortex configurations in ultra-cold atomic systems and monitoring their interactions with phonons. In principle, therefore, it might be possible to search for quantum hair directly by studying the scattering between collective excitations or phonons with finite topological charge and an analog rotating black holes imprinted into the condensate. And that, in principle, would allow those gedanken experiments to become real and allow us to look for quantum hair. Now, quantum hair may not be the only thing we could use classical and quantum fluids to try and understand. The last thing, before I end this talk, and I'm happy to see I'm doing my half hour as planned, is holography. I thought I should at least mention the word since this is your meeting. Planar ADS black hole solutions can be exactly mimicked using a non-relativistic Bose-Einstein condensate in 2+1 dimensions. An analog gravity system relating a fluid on the flat boundary of ADS spacetime to one in the volume has been investigated. The kind of things you're interested in if you're thinking about holography. The latter mimics the projection of the dynamics at the boundary and generates an effective metric that reproduces the asymptotic ADS geometry. Now, if this is just an analogy, and to construct a complete analogy, you'd have to study the back reaction to show whether and under what conditions some type of gravitational phonon dynamics emerges. There's no gravitational phonon dynamics being understood here. It's just an analogy, but it gives hope that these proposals could, one possibility could be generalizing these fluids and spacetimes to relativistic Bose-Einstein condensates. And there, the field equations for at least Nordstrom gravity have been shown to emerge. Such an extension could allow one to directly probe the relation between emergent gravitational physics and the quantum hydrodynamics of freedom at the boundary, hydrodynamical degrees of freedom at the boundary, and therefore probe what appears to be emerging gravitational dynamics in the fluid and the quantum degrees of freedom, and therefore explore holography itself. Now, I put this up here because I'm assuming the organizers are going to want my slides, and I thought I'd give some references to the quantum hair scattering in fluids and also holographic arguments in ADS here, if you want to see that. But the bottom line is, to conclude in exactly 30 minutes, while the dynamics of these systems are not precisely the same as for real gravitational systems in every case, exploring how such phenomena as back reaction imparts on their evolution may provide important clues to investigating similar problems in quantum gravitational physics. In liquids and other systems, these possibilities add motivation to continue to explore experimental phenomena, real accessible experimental phenomena, with the hope of providing empirical guidance into developing a consistent theory of quantum gravity and, of course, an understanding of holography. So the idea here is 3 different tools that might be useful in principle to understand quantum gravity, to test it experimentally, and to look for the dynamics that will allow us to get empirical guidance, which is probably going to be, I think it is likely to be essential to developing a true quantum theory of gravity and understanding ansatz such as holography and how they may arise. So that's my talk. Thank you.
Thank you, Professor Krauss. It's a really amazing presentation. Okay, is there any question to Professor Lawrence Krauss?
There was a lot there and very different areas, so I don't expect many questions. But But you know, I did provide the references for you to think about, both to the papers I talked about and to the other papers. And the whole purpose of this is to motivate you to start thinking about ways that we might actually probe quantum gravity. I'm an old-fashioned physicist, and I kind of like experiments. And so, to me, if you can't have experiments, then it's not physics.
Professor Fabiana has a question. Okay, please share your question, please.
Yeah, I have a question. Thanks for your nice talk, Clarice. And it's very powerful and strong for us, and especially for me because I am a young researcher in holograph. And you talk about an interesting point for me because, for example, the possibility of the residual gauge fields, for example, this residual gauge fields in some sense implies in a residual information or not. For example, using the holographic duality, it's possible to extract any residual information for the black hole in terms of the entropy or not. Well, I'm not sure
Well, I
about
mean,
this.
I have to say it's all quite speculative. When Frank and I first realized that this involved quantum hair, there were later papers. We suggested that, in fact, perhaps the entire entropy of a black hole could be discovered in terms of quantum degrees of freedom. And maybe there was an infinite amount of quantum hair. I think that speculation has not panned out. We had hoped that might be the case, that you might show that if you actually describe black holes as fully quantum objects, that they may have enough quantum numbers that they would account for all of the entropy. But as far as I know, no one's ever shown how that could work, and it would be nice, but I think it's as I said, no one knows how that could work right now. But it does suggest that at least it does open the possibility that is exciting, that whereas classically everything becomes invisible, it falls in a black hole, that quantum mechanics does allow you probes that you wouldn't have otherwise. I suspect that that's not going to be the entire solution of the information loss paradox, but it does at least hold out hope. Okay.
Thanks a lot for your beautiful explanation.
Okay, sure.
And thanks a lot for the opportunity to know you, not in person, but the Google meeting. I am following your work, and as I young, I see the many documentaries, and I watch and read many books of you,
Yes.
and this is was a good motivation for me to follow in the physics career.
Well, thank you.
Thanks a lot.
That means more to me than you may realize, especially at current times. It's really means a lot to me to know that I have an effect in my writing, and it motivates me to continue to write. So thank you. Thank you very much.
Thanks.
Thank you. Yes, we have other questions. Christos.
Okay.
Hi, I just want to say I'm a big fan, and I love your work, and
Yes.
it's great to see you. That's
I wish I could see you, but you're not. Your camera is not working.
I haven't done my hair today, so
okay.
I'm a bit shy. But
Okay.
but yeah, that's all. Sorry, I don't want to disturb the meeting.
Well,
I'll be quiet.
I have to tell everyone here that I think if it weren't for Christos, I would not be here today, because Christos arranged through Christos, because of events, I was able to visit kindly the university in Cyprus, Vizet and others, and that where and that caused that connection, and I think that's why I've been invited. So thank you, Christos. You're the grandfather, or maybe I should say the godfather of this whole thing.
Sure. Well, I need to say thank you
Christos.
too in that case, because I've been studying physics now since you've been here. I've made some connections with Huriye, and who's in the call right now, and I've been learning physics. I'm not there yet to understand quantum hairs, but I'm still trying to understand why a ball falls down. But step by step.
Well, it's baby steps, and I'm glad you're learning, and maybe at the next of these conferences you can give a lecture.
Yeah, amazing. Would love to. Okay, I'll
nice
be
to
quiet.
see- It's nice to hear from you, Christos. Thank you.
Okay, thank you, Christos. Ida, please share your question.
Hello. Thank you for the very interesting talk. I just had a question that might not be directly connected, but related. But you mentioned that one could possibly measure Unruh effect using or study Unruh effect using fluids. And I had a relevant question that do you expect that the Unruh effect would back react to geometry? I guess the answer is no, but I was just
Well, I
curious
don't
to hear
know.
your-
I mean, I think that's why you want to try and measure these things to see what you can learn about dynamics, or whether it's purely kinematic, and I'm very happy to say I don't know the answer to your question.
Thank you. I was just wondering, since if the Unruh effect would back react to the geometry, it would lead to some contradictions because.
Well, I
Yeah.
mean, that's the key question. All of these semi-classical effects don't have a back reaction, right? Same with even with Hawking radiation, and it's that back reaction that ultimately is going to determine how those effects manifest themselves in a true full quantum theory of gravity, and not a semi-classical theory in which gravity is a classical fixed background. And the answer is, well, I don't think anyone has the answer. If we did, I think we'd have a potential resolution of the black hole information loss paradox. But I know that I've done some work with a colleague, Tanmay Vachaspati, and others, trying to do a fully self-consistent quantum calculation of gravitational collapse with some back reaction. And in fact, we wrote a paper suggesting that black holes don't even form, that radiation is emitted before the event horizon forms. You can look at that paper. I think we're the only ones who believe it, although it has a lot of references, but citations, I mean, but it could be that the back reaction means all of these questions that are so urgent to us, and paradoxes that are so urgent to us, aren't paradoxes at all. But I agree with you. It causes contradictions, and I don't think anyone has a resolution. Maybe you'll come up with one.
Thank
I
you.
hope so.
Just one last question. So is what you mentioned about black hole radiating before the horizon shape? Does that have to do with the fact that from the point of view of an asymptotic observer, the collapse process would take like an infinite amount of time if we want to?
Well, it does, and that's another interesting question that I raised it in a paper, another paper, which I still don't fully understand the resolution of. Let me give you this paradox. And some people, my friends, Lenny Susk and others, claim it's not a paradox, but to me, I don't understand it. Asymptotically, you're absolutely right. You can't observe a black hole form because things freeze on the horizon, because redshift is infinite at the horizon as things fall into, as the horizon forms. Okay. So that's well known, and that's why they're called frozen stars in Russian, and not black holes. At least they used to be. I don't know what the new terminology is. Well, that's fine. But what about but if you allow for Hawking radiation, then the black hole, as seen by an external observer, will radiate away in a finite time.
Yes.
And now you have this potential problem that you'll see a black hole disappear before it forms. And that to me is at least worth thinking about. I'm not sure it's a paradox, but it is an interesting one to me.
Yes. Can we say that if black hole forms once all the matter has collapsed to close the Planck distance from the horizon?
Well, I mean, you're right. All of this happens. Like everything in quantum gravity, like everything, it all depends on you being exponentially close to the horizon. Because if you're not at the horizon, then there's no infinite redshift. And so everything depends when you're within a Planck mass of the horizon. And of course, that's where all of the uncertainty and all of the discussion and speculation involves itself. Firewalls, everything, all of the interesting proposed phenomena that may or may not resolve a black hole information paradox are really related to Planck mass distances from the horizon, right? That where quantum phenomena are happening.
So, I mean, even in that case, in your paper, the radiation will happen fast. I mean, the black hole will radiate away before the horizon forms, right?
Yeah, that
Okay.
it's so
Yes,
yeah,
yes.
you know, and I don't know if it's a problem or not. But in the paper with Vajraspati, you can actually see Hawking-like radiation emitting. It's a case of it's a case of essentially a scalar field, but you can see Hawking-like radiation that's not fully thermal being emitted as the system collapses. And of course, in the right coordinate system, the horizon is an infinite distance away in those coordinates, and yet this is radiating at a finite rate. Of course, there's no back reaction there, but no full back reaction. But you could speculate that the whole system radiates away before it even reaches the horizon. Now that's a nice speculation, but there are huge problems with that, and I don't want to deny it. And they are, first of all, once again, this is a scene from the observer at a great distance, but locally you fall through the horizon in a short time, and so how you could understand that gradual emission for real black hole formation it's an interesting question, but our paper raises more questions than it answers, in my opinion. But it does suggest that perhaps the canonical thinking might not be right, and I always like that because I've always been a heretic my entire life.
Thank you. Thank you for
Thank
the
you.
answers. Thank you.
Any other questions?
Can I ask a question?
Sure.
Whatever it is.
Thank you for your talk, great talk. My question is related to temperature in gauge theory and in ADS space-time.
Uh-huh.
Temperature is temperature corresponds to gravity in ADS space. Yeah.
I didn't quite understand that.
In gauge theory,
Yeah.
temperature corresponds to gravity in ADS space.
Oh, I think that's right. Yes.
Yes. If we how can I say, if there is such a kinds of relation between gravity and temperature, then what we can say other forces. I think for other forces, for instance, weak force or magnet force also have to be such kinds of features.
Well, look, I have to tell you, you're dealing with there. One of the reasons why I'm happy to say, except for this paper on quantum fluids where I mentioned the word ADS, I've never written a paper on anti-de Sitter space, because while it's a hugely interesting phenomena in conformal field theory and string theory, it's not as far as I can see, our world isn't anti-de Sitter space. And moreover, the things that matter to me, including the weak force and the strong force, on which I spent a lot of my time as a physicist, are in these are not real world situations. They're not even generally 3+1 dimensional. So if you're asking how the weak and strong force play into these scenarios in an artificial limit dimensions, I don't have an answer because I don't work on that area.
Thank you.
Okay.
I shared one question to the chat board while I was listening to your seminar. Maybe you may see it over there, but it's related about the existence of quantum hair is influencing the spectrum of Hawking radiation emitted by the black hole.
That's an interesting question. It could, in principle, it could. It could influence the correlations that happen, for example, in the radiation that come out, and therefore affect the information loss paradox. In principle, because there's no long-range fields, it doesn't change the mass, the asymptotic mass of the black hole, and therefore the surface gravity of the black hole, and therefore it doesn't affect its temperature. But it could certainly, it certainly could. Well, it has to be. It has to be give some encoding if you could find the right quantum observable, and this is the key point, because the effects are completely invisible classically. Now the problem with Hawking radiation, if it's really true and if it's really completely thermal, then there are no other signatures. But what this might suggest is that the information is not completely thermal, which is what everyone's suggesting about the solution of the information loss paradox. It's suggesting that there are correlations, entanglement, that somehow yield information that so that the radiation isn't completely thermal. There are higher order correlations which in purely thermal radiation vanish, right? Everything other than 2-point correlation function vanishes in terms of correlations in a thermal radiation. Namely, everything, all higher order correlation functions are just products of lower order correlation functions. But in the case of quantum information, you'd expect there to be correlations that are buried that are otherwise invisible. And the answer is, yeah, maybe that was the hope, but we certainly never.
So therefore, will the discrete gauge symmetry impose any constraint on the possible states or the information encoded in the Hawking radiation? And do we expect any constraints?
We certainly expect this. That ultimately, I mean, what is absolutely true is when the black hole becomes small enough, so its temperature exceeds the scale of symmetry breaking, then at that point, what's clear is that charge can't disappear because it's conserved. So when the black hole evaporates, that charge can't disappear. So one of the things you know about the black hole is that it has to emit those charges. But of course, at the latter stages of the black hole evaporation, the temperature is high enough so the U1 symmetry is restored. And then at least on that scale, there are long-range fields that are going to therefore, just like they would for a charged black hole, as you know, a regular charged black hole will stop evaporating, right? The temperature will go to 0 at some point. Again, in this case, you'd imagine, I think, that once the black hole evaporated down to the point where the temperature was exceeded the mass scale, so that the U1 symmetry was restored in the region of the black hole, that charge would be charge again, and that you might expect the temperature to go to 0.
Very plausible. Thank you.
Yeah.
Thank you very much.
And I hadn't actually, frankly, I hadn't thought of that before you asked the question, but it is interesting because it suggests you could have stable quantum black hole remnants. And that might also, well, I don't know if it would resolve the black hole paradox, but it would be interesting. Yeah.
Thank you, Professor Krauss.
Thank you. Thanks again. It was fun to have a chat. It was fun to. It's been a long time since I spoke at a physics meeting.
Thank you very much. Please don't leave because we will have a mass photo. I think Professor Bergman will announce it. So
most people don't have their cameras on, so
they should open it. Yes, Bergman.
There he goes. There's Christos.
Yes, Christos. How are you?
There we go. Now everyone who's hiding before is coming out.
Yes.
Victoria, I see Horia again.
Yeah, yes.
Okay.
Open your cameras,
I don't know why
please.
people were hiding their cameras. Everyone looks so good.
I don't know too.
They shouldn't do that. Some people still. There's Farani, Logan, Sabira. It's nice to be able to see the people who ask me questions at least. Although someone who asked me questions isn't there any longer, is she? Okay. Ida, I think her name. Okay, well, nice to see you all. Some of you. Oh, there's Soria. And the rest of you aren't coming on. So I guess you're shy. Let's take a picture. Actually, I'm gonna take a screen. Hold on, don't go away. I'm gonna take a screenshot.
Don't go away, yeah.
There we go. I got that. Thank you. It's been an
We
honor.
thank
Oh,
you,
there's,
Krauss.
oh, there's Christos, and someone was with him. Hold on, I didn't
It's
see it.
Hannah.
Yeah, yeah.
Remember Hannah?
He is hiding her. Hello.
Hello.
It's Hannah. You met like when you were in Cyprus.
Yes, there we go.
Yeah. Sure. You're missed here, by the way. We
Well,
all
thank
miss
very
you.
much.
Actually, I don't
wanna
know what
return-
everyone is
I
doing.
want to return some. Can I see a friend again? Who I couldn't see in the little picture before. Maybe just
Yeah.
maybe she's shy.
Hannah. All right, come say hi.
I'm sorry, it's probably not relevant to the meeting. Oh, there we go. Hello. Yes, nice to see you. Okay. Anyway, thank you all. I hope to return to
Thank you,
Cyprus. And maybe
Krauss.
I'd love to speak where every one of you. I'd love at some point to come to see the rest of you in your countries. I don't tend to speak much in the US anymore, but I do. I'll be in Kazakhstan later in the week for anyone who wants to be there. And anyway.
I'll come to it. I'll do it. I mean,
Okay,
no one
come to
else is coming.
Kazakhstan. Fly to Kazakhstan, Christos. I'll see you there. I'm there on Thursday, Friday, Saturday, and Sunday.
Okay, sounds good.
And then
Which
And then I'm in
city?
London, and then I'm in Oslo, and then I'm in Stockholm. So come to one of them.
Okay,
Okay?
sounds good.
Email me or text me. Okay?
I will.
Okay.
I actually will.
The rest of you are also welcome. Anyway, and Hori, it's nice to see you. I hope I had a wonderful time there. I hope to come back and be at your institution again. I'll say goodbye now, though. Thank
Okay.
you. Thank
Bye
you.
bye.
Bye-bye. Bye.
Yes, Behnam.
Thank you. Just do not leave the room. I should close the conference by introducing winner of conference prize, conference and statistics. Just a few minutes.